We will now look at a segmented parabolic reflector which is used in solar dish designs associated with a variety of concentrating solar power systems. We've created our reflector in SOLIDWORKS starting with a base parabola that follows the overall form of our as-designed system. If we impose a color relief map on the surface showing the change in local curvature, we can see that this parabola has a radius of 360 inches or 30 feet, with a total diameter of 60 feet. We now cut each mirror segment from the base parabola by constructing a grid that matches the segmented mirror pattern we want to build. In this case, we've defined a segmented parabolic reflector with 82 mirror segments, and the finished design can now be saved as an IGES file for import into ASAP. Using the CAD translation capabilities in ASAP, we can import and view our geometry from SOLIDWORKS in the ASAP 3D Viewer window. We can see that each of our mirror segments has been correctly constructed from the imported model, and we've added a small detector surface at the focal point of our solar dish. For this example, we've simulated the incident solar radiation with a simple grid of rays which are now traced to the solar dish and focused at the detector. We've added a 1/4 degree divergence to the grid of rays, and we can see the spatial extent of the source by looking at an irradiance map of the focused energy on our detector surface. Once we've completed the ray trace, ASAP lets us quickly determine the irradiance at every surface in our model, and we can see that all of the collected energy is absorbed at the detector surface. The solar dish is assumed to be a perfect reflector, but we can easily include in the model the effects of scatter, absorption, mirror and coating reflectivity, as well as detector conversion efficiency to more accurately simulate an as-built system. Now, mirror alignment is an important factor which directly impacts the collection efficiency of this type of solar design. ASAP allows us to treat the mirror segments independently, and we can therefore apply tip, tilt, and translation tolerances to each mirror in order to run Monte Carlo simulation of the solar dish as a whole. In this case, we apply a tip and tilt to an individual mirror segment to demonstrate the effect. Once the simulation is complete, we can step through the individual views created for each applied tilt error, where obviously we've greatly exaggerated the tilt for clarity. Again, we can apply an alignment tolerance to each mirror segment to analyze the effects of misalignments which might occur during the construction of an actual system on overall system efficiency. We now return to the segmented parabolic reflector we created in SOLIDWORKS. In order to simulate the effects of stress loads such as gravity or wind loading on the mirror surface, we've applied a bending moment to the entire structure using tools available within the SOLIDWORKS modeling environment. You can see that we've defined an arbitrary axis of rotation for the bending moment, and in this case have applied a maximum 1 degree bend to the entire structure. We've made no attempt to model physical deformations due to actual stress loads. We simply want to demonstrate the interaction between ASAP and the possible output from an FEA analysis tool such as Cosmos. Examining the curvature relief map we previously applied, we can see the vertical axis of symmetry we've now imposed on the parabolic surface. As we've already demonstrated, this modified surface can now be saved and imported to ASAP using ASAP's native CAD translators. After importing the now deformed parabolic reflector, we can once again trace rays from a simulated solar source and immediately view the effects of the surface deformation on the detected irradiance distribution. Note that the deformation results in a large horizontal spread in the irradiance and is likely far larger than we might expect for a fielded CSP system of this type. As an added feature, ASAP allows us to map any arbitrary surface we've created or imported. This is done by launching a user-defined grid of rays at the surface and calculating the 3-dimensional point of intersection for each ray. This data can then be stored and displayed using ASAP's standard picture window, which allows us to quickly view the sag at any point on the surface. Having created a similar map of a perfect parabolic reflector, we can easily subtract the two data sets to directly observe the difference in surface sag imposed by our simulated stress load, and we see that we've correctly recovered the physical deformation placed on the parabolic reflector in the original SOLIDWORKS model. ASAP allows us to quickly create or import virtually any type of complex optical surface and provides fast source creation, ray tracing, and analysis tools to serve the needs of the system designer.